Hello, good morning, and welcome to the High-Speed Measurement Virtual Workshop. I love that we can all be virtual here. My name is Justin Bushinsky, and I'm an account manager for Trillion Quality Systems. I want to thank you all for joining us. Many of you know we had planned this meeting at Wright-Patterson Air Force Base Museum, and it's really inspiring to see so many of you here who all continue to work professionally through these interesting times. We're here to discuss high-speed measurements with next-generation technology, using non-contact measurement, just cameras that when paired with our Aramis software can become the most powerful tool in your laboratory. In the image on the left, you can witness a Chinook helicopter crash landing at NASA Langley. And the color map is actually the images processed to reveal a 3D displacement field across the surface. So we're here to explain how you can perform 3D optical measurements like this too. And we're here to support you. Studying the behavior of materials and components during a high-speed dynamic event such as this is always challenging due to the complexity of setup and the fast data capture rates that you need. So today we're going to show you how we've become a critical tool for testing labs because of our ability to measure holistically, simply, and rapidly. And our goal is to introduce you how to set up and evaluate high-speed projects. I'm surrounded by talent today. I have with me on the call Trilion's engineering manager, Joe Horn. He's an expert in mechanical testing, and Joe will be showcasing a real-life application directly in our software. We also have a presentation from Shane Kirksey, joining us from Photron. Shane has 10-plus years in experience with high-speed applications. And finally, we'll be hearing from John Tyson, the president of Trillion Quality Systems, with his decades of experience in testing, to give us our final thoughts on how this technology can be leveraged. So let's get started. I will be introducing you to the 3D deformation analysis tool Aramis. Essentially, it's an optical strain gauge for full field strain and displacement measurements. It includes hardware and software designed together. Later in the webinar, you'll see that Joe uses the Aramis evaluation software to turn qualitative images into precise quantitative measurement. So Trillion is an American engineering firm that's been around for the last 20 years, and we specialize in the development of optical 3D measurement and analysis tools. We help our customers with application development, consulting services, and turnkey system deployment. We are a growing business with headquarters in Philadelphia and offices throughout the U.S. Each one of our offices keeps systems on hand and supports businesses locally and visits for service work and training. Trillion is the exclusive North American distributor for GOM GmbH. GOM develops the software and the industrial systems for the automated 3D coordinate measuring technology and 3D testing. And they're recognized worldwide with over 16,000 system installations. So I'd like to show you the GOM lineup of measuring systems. We're going to talk to you today about Aramis, but suffice to say, Aramis is indispensable when monitoring and analyzing the development of displacement or strain fields in time. So more on that, but we also have the Argus, which is a static forming analysis tool that yields full field strain, thickness of material, and it replaces circle grid analysis. There's also the Tritop, which is a mobile coordinate measuring machine where you can bring the machine to the part. It's great for large specimens and is even capable of static deformation. We now can look inside your part or material with our GOM CT. This is a 3D X-ray, and it's a product that has software and hardware integrated for the first time ever with a CT metrology tool, and it's best in class for resolution and accuracy. And finally, we have the ATOS. It's a 3D scanning tool used for reverse engineering, shape, and tolerancing. And what's really unique is all these solutions work together, and projects can be shared from software to software. And Trillion offers services to visit you and perform a measurement with any of these technology. Today we're here to talk about the Aramis system. So it's comprised simply of a pair of cameras and a light. Typically, labs use single-point instrumentation like LVDTs, extensometers, accelerometers, foil strain gauges. You can see the list here. The problem is that they can be painful to install and difficult to predict where to place them. For those needing to validate the numerical simulations you can see on the right, they may need many data points, and it can take a long time to set up. So finite element analysis, FEA, is a powerful way to understand your product's design. But as a reminder, it's based on assumptions. And the full field Aramis tool acts as a bridge for the testing lab to the simulation group. It empowers them, gives them a testing tool that allows them to capture the full 3D coordinate surface of the part under load, providing thousands of points for comparison to models, and getting your simulations as close to reality as possible. Our measurement in the center is extremely similar to the FEM you see on the right, and Aramis is certified for displacements as a class 0.5 or better according to ISO standards. Typically, we're a Class A extensometer following ASTM standards, and as a strain gauge, Aramis is much more accurate than a foil strain gauge. We're found by a third party to be consistently closer to the actual value because it's non-contact and it doesn't suffer the problems of imperfect surface attachment. So you end up with A-class extensometer essentially. Aramis uses a principle of triangulation, photogrammetry, to measure 3D coordinates along the surface. It does this dynamically. Just like your eyes see in 3D, the software acts like the brain. It puts the left and the right images together into a triangular 3D mesh. Aramis is capable of precise 3D displacement measurement using target stickers on the surface of your testing object. Here we have a prosthesis, and the test person is running up to 10 kilometers per hour. We're capturing it at 200 hertz, 200 frames per second. This is a pretty narrow structure, and we use very small dots here. And we're looking at the bending of the prosthesis. So each sticker becomes a 3D coordinate for us. Everywhere you put a sticker, you get a 3D coordinate in space. And we use this for point tracking in the time domain. In this way, we're able to get 3D velocities, 3D accelerations, and 6 degrees of freedom, all just from lightweight adhesive dots. Alternatively, Aramis can be used for full surfaces by way of stochastic patterning. And we can create thousands of tiny dots with just off-the-shelf aerosol paint. So the software divides up all these thousands of tiny dots into targets for tracking. And from these targets, a strain map can be measured on the whole surface. And so the software automatically identifies and tracks the high contrast of the pattern. Pretty powerful. So to sum up, our ultimate multi-purpose full field dynamic sensor, Aramis, it's non-contact, and you can avoid surface preparation, set up very rapidly. It's full field. It's going to give you insight and an understanding of your part that you wouldn't get otherwise. It's going to give you displacement and strain at the same exact time. It's very powerful. You're able to move from micro to very large scale, and here I mean maybe 1 millimeter to several meters in size with a single tool. It's very flexible. We're material independent, and this allows you to move from rocket motors to thin plastic films to human skin, and we can move from static to very dynamic oftentimes. Oftentimes it's the same equipment, and it's the same test workflow throughout, which is really nice. And we have integrated and massless vibration analysis, so we can see 3D deflection shapes. We're also very critical, absolutely critical. Any model will need validation, and we can conduct multiple data alignments with our real-world measurement. And so thousands of points can be compared to your FEA. So this is a pretty powerful tool, as you can see. Aramis has been used to examine a diverse range of different materials and specimens, looking at evolution of uniformity of strain, crack tip, crack propagation, detecting damage development, composites, structural deflections, high temperature strain mapping, dynamic vibration, all over the place. If you look on the screen, you can see the Chinook helicopter, a steel bulge test, an adhesive shear test. There is no standard application. There are many, many different tests performed with our product, and driven by you as our customer. So your standard is our standard, and we'd love to help you develop your application. So this is the point of the presentation where we can choose our approach as to what we want to see because our tool is so robust. But for the purposes of our presentation, we're going to go through the high-speed testing, vibration analysis, and the FEA, and sum things up really nicely for you. So let's take a look at high-speed testing first. So we're going to take a look at a door slam test. Most of you know the high-speed test of the impact door slam. The door is often slammed maybe a meter per second or 2 meters per second, just depending on if you've had your coffee this morning or not. But the most important information about this is the impact of the door relative to the chassis, next to the lock. So let's take a look at this. This will be captured at 1,000 frames per second. And you can see, if you look closely at the image, there's dots on that chassis and dots along the door panel. And so we will make the chassis our rigid body and a process in our software called rigid body motion correction. And so we can make our displacement measurement relative to the chassis and effectively isolate the door panel movement from the global motion of the vehicle as it slams. So let's take a look at this video. Here we're using retroreflective point targets, and they reflect the light directly back to the spot where it comes from. This gives the advantage of short shutter times and reduction of motion blur. We're going to use a trigger with a light gate, and then we're going to position our sensor until the laser beams fuse to find the center of our measuring volume. I'm going to open the door. Anywhere we put a sticker, we're going to get 3D data. So place them where you need information. We're going to go into our software and set this to collect 500 images at 1,000 frames per second. And when we slam the door, it will trigger the system to collect. And you can see the pulse of the light on the system there, and it's collected, and we can go back to the computer. And now we can get into analysis. So we can select multiple points along the door panel for vector displacement measurement, and we can select individual points for discrete displacement measurement, and it's automatically plotted on the diagram on the right. You can see the velocity and the displacement in the Y direction here. And you can see some interpolation here on the door. I'll show you later how we're able to capture the full door and its vibration. Now let's look at crash testing, a vital part of the automotive world. And so many crash labs use their footage as a qualitative result. So many of them already have cameras in use. Aramis can make that quantitative. This is a seat and belt test and a simulated sled test. We place tracking dots on the sled, the seat, and the dummy. We'll be using the sled as our rigid body for motion correction, as I mentioned before. So with this, we can measure displacement and velocity of any isolated component. Here's the video of the test and the typical qualitative images. And here's the evaluation of full motion. And the vectors tell a story of magnitude and direction. And we can zoom into the head and add a local coordinate system for tracking pitch, yaw, and roll. Nice analysis of the dummy head here as it rotates. In the software, as we conduct these inspections, a diagram will automatically plot our measurement. And any of these measurements that you see, they're not just pretty pictures. They can actually be output into a CSV file. And we also can track the trajectory of different components. Nice analysis of the head there. We also have Aramis high-speed systems that are integrated, and we're compatible with a wide range of leading brands. Today we have Photron with us, and they're really best fit for our applications. Our system, as you can see here, is two SAX2s I have just up on our screen. These are Photron high-end, high-speed cameras. The system consists of a rigid bar, a light, and a synchronized trigger pulse between the cameras. And so it's really robust, but yet flexible sensor design, and it can measure full field strain and displacement maps, equivalent to thousands of strain gauges. Let's take a look at some drop tests conducted with Photron cameras. Here we're going to sample at 20,000 frames per second in order to capture the impact. We're going to drop a couple of, I guess, consumer products that you're all familiar with, cell phones, and you're going to notice what they are. You can see on the back on the right side of this picture, you've got some camera and some motherboards in here. What we want to see is what happens when we drop these. So let me click this to start it, but our drop test will feature a rigid body motion correction that's applied to the surface mesh. So that's to negate the translational motion of the drop and only look at the relative motion of the surface mesh. Because we're capturing with non-contact optics, we can place down different types of instrumentation, such as a section line. The section line is applied to the surface internally there, and we can show the shearing motion because the back of the screen and the internal components are moving. And that profile at the bottom here, this diagram shows that profile all along the side of the phone there. Here we can actually inspect two-point distance, and you can see two different inspections here on the camera and here for a different headphone jack. And we're looking at the distance between the motherboard and the actual component here. So you can place down, when you have this speckle pattern, you can select anywhere for a discrete point, and you can do a two-point distance. Here's a drop test featuring just a vertical orientation of the phone. What's interesting about this is when we're dropping it, notice where the majority of the strain is. This is going to be a nice major strain measurement. And every time you've dropped your phone, you're going to fear that this happens, and boom, there it is. Right at the corner, it seems to be always the place where my phone cracks when I drop it. Interesting to see that live. Nice buckling going on there. Here we have a really high-speed material test, a compression test, and there's very little literature regarding deformation behavior at strain rates 10 to 500 strain per second, and we can utilize high-speed cameras. The Aramis high-speed system can be used to quantify the surface displacements and the strains in 3 dimensions over the entire field with just great precision. And so we can get the behavior of metals during high-speed dynamic compression events like this that can typically be challenging. Let's look at a bullet impact on glass. This is a major strain at 1,000,000 frames per second. And so this is about a 4 millimeter thick piece of glass. And we're shooting a pellet through it that's been stochastically patterned. We actually can see the propagation of strain across that surface before it even begins to crack. Really cool looking data here. And here we have a rocket firing, and we're interested in the rotations of the rocket as it's first released from the nozzle. So once it gets up and going, they understand what happens with the rocket, but once it's released from the nozzle, they're interested in seeing the rotations of it. And so we placed up, you can see in the background there, we've got a rigid body, this piece of wood that we've placed up in our field of view, and put some dots on it, created a rigid body to be able to do these displacement measurements and look at the 6 degrees of freedom all along the rocket. Again, these are just lightweight stickers that we've placed on here for tracking. The software automatically identifies them. Okay, so we've finished up our high-speed testing. Let's jump into some vibration analysis. So earlier we saw the door slam attempt with the impact test. And usually you're looking at the penetration depths and function of the door seals and the door lock. But we can also look at frequency analysis. And the way we do that is we use the stochastic pattern on the outer panel of the door. We're able to get full-scale measurement of the displacements. And that enables us to get the door frame and the window pane all together. So here we're combining this with point measurement on the chassis. Again, we did this last time. You might remember. You see these dots all around the chassis of the vehicle here. And we can correct for any global movement in our project. So in this case, the Y direction in the automotive coordinate system is going to be positive, will be towards the cabin, and the negative will be bulging outwards. You can see that nice looking color map there that explains that. And then on the right side, you see that we've dropped down a couple of points. You can select any point you like as a discrete location, and it automatically plots in the diagram and can be output into CSV file. We can actually take all that displacement that occurred in all three directions and bring it into the frequency domain. And so the diagram here shows that envelope of the frequency responses of all the points on the outer door panel. And then the 3D diagram shows that associated vibration shape. And so you can see we've isolated the Y direction here, and we've chosen, you can see the peaks. It just is apparent to you, the different peaks and the amplitudes. You can select the peak here at 31.2 hertz, and we get to look at the vibration shape of the door panel at that frequency in this direction. So that's pretty powerful. We also can do the same by selecting another peak. Select a different peak, and we get another nice visual to let us know what's going on. And this is fully rotational, and you can get a nice look at it in different directions, so you can see what's happening with your part. This is a truck cooler fan that operates at approximately 2,000 RPM. Our measurement here is at 1,000 frames per second. It's rotating. So this is really cool. We can do rotating parts. So with a quick preparation on the component, we put down sticker dots on the blades and on the center of the fan, and we're going to drop in and take a measurement. So our measurement is done while rotating, and the 3D displacements of the measuring points on the blades of the fan and the housing are shown here. So a rigid body motion correction has been placed on this fan. And we put it on the center point here on the base of the fan so that we can look at just the fan and understand how it's moving against itself here. So the rotation frequency was set so that the speed multiplied by the number of coils in the motor would result in approximately 85 hertz amplitude. So we should see that. And let's go ahead and check on it. We're going to bring this displacement data. This is our displacement data. We're going to bring into the frequency domain now. Here it all is, and across time for all three spatial directions. Remember, we're always capturing in 3D. And we can see that first mode of vibration at 85 hertz, as we predicted. And as we click on that 85 hertz, we're actually able to see the different modes associated. So here we've selected the XY and the Z, and you can see a nice breathing mode here and sort of a twisting mode here on the fan. And it's revealing as to what's going on. So it's a nice vibration analysis tool built right within our software. So let's take a look at the benefits for vibration analysis. So we're non-contact. We don't need the wiring. It's really fast setup. You just put stickers down, and really durable measuring points you can leave on and measure again and again. And we can synchronize with your CAD, synchronize with your FEA. Each measuring point will provide 3D displacement results, and we can do full field comparison with that FEA data. That capability to be able to do rotating components is really, really powerful. Okay, so let's jump back out. I'm going to finish here with FEA validation. We've gone through some high-speed tests and some vibration analysis. I'm going to jump into a little bit of FEA validation in a really quick way here. So let's take a look at a video of a wrench. And so we're going to have an engineer come down here with a wrench that's been stochastically patterned and twist down on a bolt. And you see that pattern there. It's going to result in our data as he twists on that bolt. Okay, and we've brought in the CAD to align with it. And we can look at the widening measurement of the wrench. And so here's the simulation. And we can actually do a comparison and do a deviation map. And so there's some differences here. This is interesting. Let's take a closer look. So Aramis gives us the full field requirement that you need for your FEA validation. You notice the slippage. And take a look at this video again here. You can notice the slippage on the wrench right here. So it's actually slipping. And so, I mean, this is a great example of why adjustable wrenches are probably more effective, but it's also just really intuitive to see and to look at here. The simulation is not understanding the slippage at all. And the reality of it is that it is slipping, and we have a boundary condition that we need to adapt for. So here we have our simulation of where there's just perfect contact in a perfect world. And then here we have our deviation between what we just previously saw in the simulation. So we can see those differences here. And this is how quickly and efficiently we're able to jump into an FEA and do a comparison. The Aramis reality and the simulation are aligned, and then you get that nice color map. And we work with all major FEA software, ANSYS, LS-DYNA, Abacus, and most file types, STL, UFF, IGS. So we're really fast and efficient at this. And Aramis will speed up your validation process. All right, so let me now jump back out and into a different portion here. So we have free software, GOM Correlate software. And this software, you can import 2D images and perform a measurement for free. This software also acts as a 3D evaluation software and has sample files inside of it. I would encourage everyone on the call today to download your free copy of GOM Correlate. You actually now can try the GOM Correlate Professional for 30 days for free, and we'd love to help you conduct a measurement in your lab. At this point, we're going to open up for any questions you might have, and then we're going to turn things over to Joe for his live software and system demonstration. Does anyone have any questions?
Thank you very much, Justin. This is Jack Irwin working with you today. I just wanted to read through the questions that have come up so far. We had a question from Nin George, which I can answer for you. How can we get a copy of today's webinar presentation materials? We will be passing those presentation materials out to you. We'll be sending a follow-up email with all of that information, and the presentation itself will be posted on YouTube. And then I'd like to move on to the next question here, which I will ask to Justin. What is the maximum distance Aramis can be from the test article? Justin, could you go ahead and answer that question?
You know, what we have is we don't really have any kind of thresholds on what we can and cannot do. So we could be several meters away with no problem. In fact, we often find ourselves in situations like for instance, a wind tunnel, where we have to be out of the airflow, and we have to be standing back several meters away to be able to look at maybe smaller fields of view. And that's no problem because we simply adjust our lenses on our system to maybe look in a more parallel way and confine our field away or our field of view. Or we can have a more wide field of view with wider angle lenses. And so that enables us to effectively, if you think of a triangulation of points on the surface, you can spread your cameras out further or closer together and further away or closer to the part, and you're able to triangulate points along the surface. So I'd be interested in learning more about your application, and it sounds like we might need to stand off a distance from your article and maybe look at something smaller. And I think that that's something that we definitely could look into, and it would be very, very feasible.
Great. Thank you, Justin. All right. I'd just like to remind everybody to please ask your questions in the Q&A. We're getting some questions coming in through the chat. We'll address them, but I just want to go through these the best way possible here. So we've got these two, and another question has been from Aku Bahari. What is the highest data sampling point frequency? So essentially, how quickly do we record, Justin?
So I made a distinguishment between our Aramis integrated systems and the using third-party cameras. And so the GOM integrated systems can capture up to 2,000 frames per second. And above that, our technology, our software, has been shown to work for up to 5 million frames per second. We're really only limited to what's out there in the market as far as cameras go. And I showed you an example of a 1 million frames per second event. This is an extremely transient event. We're often used for split Hopkinson bar type of work, which is in the hundreds of thousands of frames per second. At this point, there's nothing we can't do when it comes to sampling.
Very good. Thank you. And then another question from Aku Bahari. What is the lowest limit in measuring displacement?
So we're going to be at a displacement of micron or sub-micron level for most of our measurements. If we look at a typical 1 meter field of view, we're going to be between 2 and 7 microns of sensitivity and displacement. And so we have a linear relationship between our field of view and our sensitivity. And as we decrease our field of view, our sensitivity gets higher. And so if we're at, say, for instance, a 100 millimeter field of view, then our sensitivity will grow even better to be on the order of sub-micron level, if that makes sense for you.
Great. All right, thank you. We'll answer one more, and then we will have time for more questions after each section of the webinar here. We just want to make sure we get through the content. So we'll answer this one from William Coulter. This one should be pretty open and shut. Was the frequency analysis done with an Aramis or using a different piece of software? So this would have been that ODS module that you showed, Justin.
That's embedded right into our Aramis software. It's something that we can do just by selecting the surface component. We're able to launch a vibration analysis tool. It's built into our software that automatically will give you that visualization. It's fantastic.
Great. That is a good point, Justin, and it's important to note too. I just had a note from John Tyson here, who's also joining us for the call, that we can export this data to any other vibration analysis software, Emiscope, what have you. So at this point, we're going to move on to our demonstration with Joe Horn. I'm going to go ahead and close out the Q&A just for now. We'll have more opportunities for questions later. Joe, I'm going to go ahead and unmute you. Okay.
Okay. Thank you, Jack and Justin. Good morning, everybody. Today I have with me two SAX2 Photron cameras. They can go up to 12,500 frames per second in full resolution, which is 1 megapixel. They can also be cropped to a lower resolution to go up to over 1 million frames per second. The test article we are testing today is a fan. See here we have a fan here. There's a speckle pattern on there. So what we'll do is we'll be doing a hammer hit with it, and then we will record at 12,500 frames per second. So if we can go over to the Photron software, and then you'll be able to see a live image right from the software there. So let me just turn on the lights here. Okay, so you see that here now, once the lights are on, you see that full field stochastic pattern with me. And just to show that it's live here, I'm going to rotate the fan blade. Now, what's important to know is that these two cameras are synchronized together, and they are calibrated together. So the Aramis software knows exactly where the one camera is in relation to the other. So that this way we can do 3D full field analysis on this. So now when we go over to the Photron software, everything it tells you all the information that you have set up for the test. We're going to, we have different triggering modes here, start, center, end, depending on your test. For this one, we will just do a start trigger. And you see here we have recording at 12,500 frames per second. We are able to control the shutter speed depending on the test and how much light you have. And you see that the resolution here is 1 megapixel. We have 3.5 seconds of recording. And now once we go here to record, our cameras are now armed. So now when, we are able to use the push button in order to capture this data. So I'll make sure my alignment's okay here. And I have with me this hammer, which I will impact the blade with. So it's now done recording, and it automatically takes us into the save mode. So now in the save mode here, we can play back our test and see what images we want to save. We can either save the full buffer, or we can crop down the image. So we can scroll through, and you see that impact there. Now you'll see here that the blade is now rotating after the impact, but we don't care about this. We can do what's called, as Justin mentioned in his presentation, a rigid body motion compensation. So even though our part is moving in our image, we can still track that full field here. And so we are able to tell it which images we want to save. So we will say, we can save it from this image here, and we can play back. And we can watch that high-speed playback here at 250 frames per second. And you'll be able to see here that we have about 44,000 images recorded during that short duration there, during that 3.5 seconds. So if we want to stop there and we want to save that image, now we'll be able to see that we can just save a small buffer. Instead of saving the entire memory of the camera, we can just save a small portion of that. So to save time here, we do have the same test here already opened in Aramis. So what we have here, we have our left camera and our right camera. Let me switch between them. And when we open the Aramis software here, we have our left camera and our right camera here between in the software. And now when we toggle through, we'll be able to see that playback of that hammer hit and then the dampening of this blade here. So again, that full field stochastic pattern will be tracked throughout this analysis here. So the software can intuitively detect the contrast level of these pixels and give us a full mesh. So when we turn on our mesh here, you'll see this pink surface here is showing us our 3D mesh there. Now you can see that the 3D shape to the blade is not exactly a flat plane. So now if we go ahead and we can turn on the mesh structure, everywhere where you see the cross-section between lines here is a data point. So we're getting thousands of data points over this entire surface here. So now going through the playback, we can now tell the software what inspections we want to see, whether it be displacement or strain, what have you. So going here, we can say now, let's take a look at our displacement in the Z. Now, and just to show you our coordinate system, we can see that the Z-plane is normal to the surface here, with our X being, or our Y being axial along with the blade length. We also have another component here, which is called the hub. Now we're doing our rigid body transformation to that. So now when we do our playback here, you're seeing as the blade as the whole fan assembly is moving, our coordinate system is moving with the movement of this hub here. That way we can make sure that our coordinate system is always aligned appropriately to our blade. So let's go ahead and take a look at, let's say, displacement in the Z direction here. So this is a full field analysis. You see I have a few labels drop down there. Now as we go through this you're seeing the color map change. So I can fix the legend. And now you'll see that the color map is changing here over time. Looking at these 3 points I have placed down here, we can look at our diagram and see a time history of these displacements here. So you see that at impact, there is a large deformation. And then we're seeing the dampening over this half-second test here. The 3 points here are labeled out, and they're plotted simultaneously. Clearly, the point by the hub here isn't moving as much out of plane, and we have by the hammer impact here at the edge of at the blade tip, we're seeing the highest deflection out of plane. So now what we can do inside of the Aramis software is run this ODS script here. So what this ODS script will do is it will transform the time domain into the frequency domain, just as you saw in the presentation from Justin. So we just select the surface where we want to do this the script to, and then when we run the software, it's now going through all the images and transforming them into the frequency domain. Okay. On this pop-up here, we see that in the top left, we have our displacement map over time with all 1,000 data points. And let me share this. And here we go. So now you should be able to see this map here. We have our displacements over time of all 1,000 data points over the surface plotted together, and then we have our frequency spectrum on the bottom left. If I say, let's just take a look at just the Z, we can now say, go to this frequency here, and now it will show the mode shape at whatever frequency we change to. And we can toggle between the different mode shapes and peaks that we see here. And that will tell us what frequency we see here. So we see in the top right at what frequency this mode shape is happening at. We can overlay it onto the image and see how it's behaving on top of this image here from the video. We can then go into the other directions and see what's happening here. Or we can do them all at once. So when we close out of that, and then I can go back to the share button. Going back here to the Aramis screen, we can now create inside the software report pages of whatever we have available for us. So let's say we want to make a displacement in the Z direction report page and video, so we see the playback. What we can do is just quickly go into our report module. And now we can create this video. Okay, so now what it's doing here, it's taking all the images here and creating this video. So it's you see here that at the bottom left, it will tell you the status of it. So we're almost completed here. So we're creating a 20-second video, and then when we go to the report page, we can then export this video as an MP4 format or AVI so that we can then embed these into presentations or show them inside of our report there. So here, then we can now play back this video. So now we're seeing the playback of this test here of the DZ, and we have other report formats that we can go through to show the plots as well as with the video here. So if we want to do a diagram plot of these 3 points, we can call this and now this plot here is now inside of our report page. Now going back to the inspection workspace, we can continue on with our analysis. If we wanted to do what we call a section line, we can by constructing a section line here. So you see there's a lot of options inside the software, inside of the different menus here. So there's a lot that you can do with it, as well as with the scripting module. So creating this section here, we can now place it. Okay. So now what it's doing is creating this section, this cross section here across the blade, across the entire test here, all 6,000 stages. Now what we can do is we can inspect the section for displacement in the Z direction. And now it's plotting this DZ over time. So when it's done computing here, we'll be able to go to the diagram and see this cross section here being plotted with DZ across the entirety of its length. So that way we can see how the vibrations are moving across this blade here. And now, if you see here, we also have in our iInspect tool here, other than our displacements, we have other options to choose from, such as our strains, coordinates, and other displacements, such as the magnitude of displacement, as well as other directional displacements, like in the X or Y direction. We're limiting it to the Z direction here, so that way we see just the out-of-plane displacements as they go across. Okay. So the videos that we create then can then be exported and then placed directly into PowerPoints and then exported, and we can even play them live inside of our software here. So now I'll open this up to any questions that any of you may have based on this quick analysis here of this blade hammer hit test.
Thank you very much, Joe. I'm going to go ahead and open this up to questions, like you had mentioned. I'd just like to remind everybody, I know some questions have been coming in through the chat. Please ask your questions in the Q&A section of the Zoom software here. That way we can answer them and you all can see them effectively. So let's see, we got a couple questions that came in. One from Gregory Redmond. He asks, Joe, does the test item need to be in the full view of the cameras through the whole drop of a drop test? Good question there.
Good question there. So it does not need to be in the full view of the drop test. As the component comes into the frame, we'll be able to track that throughout its as soon as it impacts, and then we'll be able to do the analysis on impact. So when the speckle pattern or your part with dots in there come into view, we'll be able to track them throughout the test.
Okay, another question from Gregory. Is a light source required, or is natural light fine? Natural light will work just fine. It just depends on the frame rate as well as the sensitivity of your cameras. Sufficient at the frame rate you are recording at, and you can certainly run with that. Thank you. All right. Is the mesh density in GOM linked to the speckle pattern density automatically? So I'll repeat that question. Is the mesh density in GOM linked to the speckle pattern density automatically? So we have full control of the density of our mesh there. It's a parameter called point distance. So essentially we are spacing the points at a pixel length across there. So we have we can fully control that depending on what you need from your test. If you need more data points there to match, let's say, your FEA model, then you can certainly add more points in. Okay, another question that came through. Let's see here. Got a lot of questions about outside lights, outside applications. They ask what the lighting requirements are if they want to do these tests outside, for instance. Is there any limitations there?
Well, barring any weather, you can certainly test outside. The natural light will work fine. Again, just to repeat what I've mentioned earlier, as long as you are recording at a frame rate that the natural light will be sufficient, then you can operate with that.
Okay, another question that's come through. Can you export data sets for forming limit diagram from a bulge test or Nakajima test into Excel?
Yes, and we actually have a script for the FLC to get that data there. So we have we can do it inside of the Aramis software, or we can export that data as well. So ideally, your cameras want to be between 15 and 35 degrees. So with those parameters set, we can then separate our cameras as far away as we want, depending on the size of your object. So if your part's larger, then you may need the separation between them to be larger, but still maintaining that 15 to 35 degree camera angle.
Another question that's come through here. How do you put the speckle pattern on the test object, especially if it's odd-shaped?
So there's many methods of applying speckle pattern. There may even be a natural pattern on your part. Typically, the easiest way to do it is with a can of spray paint. We just speckle on the dots after placing a white base coat on. We can then use also stamp pads or perforated sheets to give us a speckle coat. The main thing to keep in mind is that it needs to have contrast and a 50-50 coverage between the black and the white.
Okay, very nice. And then we'll do one final question here before moving on. Are there any limitations in operating temperature?
So you're limited to the camera operating temperatures. However, if your test is, let's say, inside of a thermal chamber, we can look through a pane of glass so that we're working with room temperature. If you cannot work with inside of a temperature, let's say you're in a large environmental chamber, then we can enclose the camera system so that it has its own environment inside of there, so that we're not limited by the factors outside of there.
Very nice. All right, we will get to more questions here as we go throughout the presentation today. I'm going to take the opportunity now to pass things off to our colleague Shane Kirksey from Photron. I invite Shane to go ahead and share his screen and tell you a little bit about some of the cameras that we use to perform this measurement.
All right. Well, thank you, everyone. My name is Shane Kirksey. I'm an application engineer with Photron. And Photron's been around for quite a while. I've been with them for the past 10 years and seen a lot of different applications. We always enjoy working with Trilion. As they mentioned at the beginning, they can use a lot of different high-speed cameras, and but we know that the Photron high-speed cameras, just like everybody else, they have benefits over others, and Photron focuses on a few things, and other high-speed camera companies focus on some things, and everybody has their place in the market. So what I want to talk about a little bit today is things to consider when choosing a high-speed camera. Let's see if I can advance. There we go. So there's a lot of things that you can that can affect your test, that can affect what you're looking at when purchasing a high-speed camera. And frame rate and resolution are generally driven by the test itself. So in a perfect world, everyone would be able to record at many megapixels at faster than you could ever imagine. But there are some limitations in sensor design that keep us from doing that. Monochrome or color. Monochrome, as I'll say later, is always going to give you a more sensitive camera. But for some, and for DIC, generally monochrome I think is preferred. But for some applications, some tests, you might want a pretty picture. You might need to get some color data out of the image. So we, of course, have color cameras as well. Minimum exposure time to stop image blur and to really get a fast-moving object to be as crisp in the image as possible. That's when minimum exposure time comes into play. We'll talk about that a little bit later. Internal memory. I mean, we have cameras with up to 128 gigs of internal memory. We have some cameras that can actually stream to a 2 terabyte drive. So there's lots of different memory options. Sometimes you need to record for long periods of time. Sometimes a fraction of a second is all you need. So lots of different memory options for the cameras. Data offload speed, it's always, kind of the high-speed camera guys are generally the ones that are slowing down the repetition of a test. So now Photron cameras, as well as some other manufacturers, have 10 gigabit offload. So we can get the data off the camera and to the control PC quickly. We have what we call a fast drive, which is essentially a solid-state drive that plugs directly into the camera. So if you need to take a second test right after your first test, you need to get that data off as quickly as possible. You may not want to wait even the 3 or 4 minutes to offload to the PC. So you can actually, with the fast drive, offload 1 gigabyte per second. So if you've got a 64 gig camera, you can actually get that data off to the fast drive, all 64 gigs, 12 bits of data in roughly a minute. So extremely fast offload speeds with the fast drive, which again allows you to get more tests done per day. At the end of the day, you can offload that 1 terabyte, or we even have a 4 terabyte fast drive. At the end of the day, offload that data to your PC and analyze it, the next day or overnight, if you like. And those are hot swappable. So if you fill one up, you can pop another one in and continue doing your tests. Camera size, there for a while, a couple of years ago, all cameras were just getting bigger and bigger. Now that sensor technology and memory technology has improved, the camera sizes are getting smaller, which is nice. Light sensitivity is very critical. That's actually what I'm going to talk quite a lot about today, is light sensitivity and how it impacts your test, how it impacts a lot of factors with your test. And then support. We work well with Trilion. All of our customers that have Photron cameras and Trillion systems are extremely happy with the support, the excellent support that they get from Trillion as well as Photron. So I think we have a great team there. All right, so light sensitivity. So there's a lot that goes into light sensitivity. Someone asked the question earlier about, can you do this test in natural light? And as Joe mentioned, absolutely you can do it, as long as the frame rate and the exposure time allow that the ambient light is sufficient. So in that case is a good example of where light sensitivity plays a factor. Now, most high-speed camera companies design their own sensors, so it really comes down to what is the latest technology in sensor design, and what is the quality and efficiency of that design to give you the sensitivity that you need. So here for a few minutes, I want to talk about some of the factors that impact light sensitivity. And then when you have a light sensitive camera, there are some other things you need to overcome. And we have a couple of features that I'm going to talk about as well to overcome some of the adverse effects of a very sensitive camera. And then we'll talk a little bit about support as well. So light sensitivity is typically presented as an ISO value. So the higher the ISO value, the more sensitive the camera. But I'll tell you right now, we should all be very skeptical of any ISO value that is provided to you, including one from Photron. And the reason for that is in the ISO specification, there are a few different ways that you can measure sensitivity of the cameras. And every manufacturer is of course going to choose the measurement technique that benefits their camera, right? So so just be skeptical, be wise when you're choosing a high-speed camera. So there are some ISO measurement techniques that allow for adjusted LUT curves, lookup table curves. So whenever you are looking at comparing high-speed cameras, we always recommend, if you can put them side by side, do that, that's great. If not, just have similar tests. Make sure that your gain and gamma, brightness and contrast are all linear, all set to 1, or no gain, no brightness or contrast. And that's going to give you the most representative or fair comparison between cameras. And it's going to give you generally the best image quality as well. So so that's something, just be skeptical, do your due diligence when you're comparing high-speed cameras. Again, for light sensitivity, for some applications, this can be the most critical consideration. If you're in a light-starved environment, maybe you're looking at into some type of vessel. Joe was talking about into a wind tunnel. Some wind tunnels are huge and they have huge viewing ports. Some wind tunnels are small and the viewing ports are very small. And you're limited to, for example, how much the size of the lights that you can actually put through those viewing ports. So for some applications, it's critical. For some applications, you're using a lower frame rate, it's not as important. Light sensitivity also impacts your ability to use a short exposure time. If you're going down to, the Photron cameras go down to 159 nanosecond exposure time. If you're using a very fast shutter speed, then if your camera is not very light sensitive, you're going to have to pour a lot of light onto that object. And in some applications, if you're looking at a biological sample, well, you're going to cook your sample before you get your high-speed data taken. So if you're using these short exposure time, generally a more sensitive camera is beneficial. Allows for lenses to be set at higher f numbers, which allows for greater depth of focus. A perfect example is what Joe just showed us. you're looking at that out of plane movement of that fan blade. Well, if you have a very shallow depth of focus, anything that's out of plane movement is going to go out of focus. And of course, if it goes out of focus too much, well, then your speckle pattern is just going to be a blur. So if you can have a very sensitive camera, you close the aperture of the lens as much as possible, that's going to increase the depth of focus. So any of that out of plane distortion is going to stay in focus, which is very, very critical in some applications. And it reduces the need, as I mentioned earlier, for additional lighting, reduces expenses, power consumption, space requirements. I'm sure some of the those listening to this presentation go back to having banks of halogen lights, and it created enough light, but created a lot of heat and created safety concerns as well. Took up a lot of space. Nowadays, they have very nice high-intensity LEDs, which I believe is what Trilion uses mostly, and very efficient, small, but is also very bright. And here's just an example of depth of field. So this is just a Photron camera with the aperture of the lens stopped down on the left-hand side. You see the depth of field is a couple of inches, and then on the right-hand side, the aperture is probably wide open and a much shallower depth of field there. So now going into some of these specific factors that impact light sensitivity. The design of the camera sensor has perhaps the biggest impact on light sensitivity. So here's a list of some of the most critical design factors, and we'll look at these individually, but pixel size, fill factor, I'll explain that, micro lenses, monochrome versus color, as well as sensor gain. So now looking at pixel size, so it seems obvious that when you're looking at pixel size, that a larger pixel would automatically be more sensitive than a smaller pixel. And if you're looking at two sensors of the same generation, that is almost always true. But today's sensors, the newer generation sensors, have some design changes in them that will actually allow very high sensitivity with smaller pixels. So a larger pixel does not always equate to greater light sensitivity. But each sensor is comprised of a matrix of pixels, which is going to determine the resolution of the sensor. Kind of the industry standards are 1 megapixel, full HD, 1920 by 1080, and now they're getting into 4, 5, 6 megapixel sensors. So the sensors are growing in resolution. So in general, again, larger pixels are more sensitive, but we'll look at the next factor, which is fill factor, and why it is now possible for smaller pixels to be more sensitive. So fill factor is, as you see here, the ratio of light sensitive area versus total area of an image sensor pixel. So if you look at this pixel, and let's say that the pixel size, the surface area of the pixel is 20 microns by 20 microns. Not all of that surface area is actually sensitive to light. So you see here that as the incoming light hits the pixels, some of it is going to make it all the way to the photodiode in the pixel. But there's other electronics in the pixel that actually bounce those photons back, and therefore the entire surface area of the pixel is not light sensitive. So for example, if the surface area of a pixel was blocked, half of it was blocked by these electronics, the fill factor would actually be 50%. So only 50% of the surface area of that pixel would allow photons all the way down to the photodiode. So the size of the pixel and the size of the photodiode are not the only issue here. Embedded in the pixels are these electronics, transistors, and electrodes that are not light sensitive. So the size and quantity of these transistors electrode will negatively impact the fill factor. So nowadays, these electronics are getting smaller, so fill factors are going up. But there's another thing that allows the light sensitivity to increase, and that's effectively increasing the fill factor of a pixel. So nowadays, many sensors have micro lenses on them. And a micro lens is simply a lens that goes on the top of each individual pixel. So now what it can do is now these photons, as they come and they hit the surface of this pixel, some of these photons that were going to be rejected by these electronics are now bent into the photosensitive area of the pixel, effectively increasing the sensitivity of the pixel. An interesting point on this is, as we're talking about newer generations of sensors, is that historically micro lenses could only be used with pixels of 10 microns or smaller. 10 microns or smaller. Nowadays, there are many sensors that have larger 20 micron pixels, 26 micron pixels, and Photron is now utilizing a almost brand new micro lens design that allows for micro lenses on 20 micron pixels. So now our larger format sensors are going to be more sensitive than ever before, and we're very proud of that. So micro lenses effectively increase the fill factor of the sensor. Now, monochrome versus color, I'm not going to talk about this very much because with DIC, most cameras are going to be monochrome. But essentially a color sensor is just a monochrome sensor that has this color filter array. So over each pixel, you're going to have a color filter. There's different patterns. The most common one is the Bayer pattern. So in a 2x2 pixel kernel, you're going to have 2 pixels covered by green filters, 1 covered by a red filter, and 1 covered by a blue filter. And so these are going to essentially filter out some of the light, and then there's going to be an algorithm that goes on that that is going to create a color image. Again, the quality of this algorithm plays a key role in the sensitivity and the image quality. But just remember that when you add this color filter over a pixel, over a sensor, you're going to have about 1/3 to 1/2 the sensitivity of a monochrome camera. So I don't want to talk about that too much because, again, I believe most of you listening are interested in digital image correlation, which monochrome cameras are going to be best suited for. Now, each sensor does also have a cover glass. So now this cover glass is essentially a piece of glass that is permanently fixed to the front of the sensor. It protects the sensitive sensor electronics from physical damage or contamination by particulates. It's important to understand that anything positioned between the incoming light and the light collecting pixels will have an impact on the number of photons that reach the sensor, thereby affecting the overall sensitivity of the camera. The cover glass is no exception to that. The quality of the glass and its coatings determine the extent of the impact of light sensitivity. So we mentioned coatings. With most cover glasses, there's 2 coatings that you have to be concerned with. There's an anti-reflective coating on one side of the cover glass, and on the other side of the cover glass, there's a near-infrared coating. So as you see here in this slide, with this color camera, the color camera is sensitive to near-infrared light. So even though the sensor is sensitive to this, our eyes are not. So if we were to not have this near IR coating, we would see this image that is more skewed into the red because of the infrared light. So this IR coating blocks out this near infrared light to give the color, make the color rendition more natural and more similar to what our eyes are going to see in a color image. But again, color cameras, less sensitive, less necessary for digital image correlation. And last but not least, I want to talk a little bit about sensor gain. So we were talking about image quality, we're talking about, sensor design. So essentially one of the main purposes, main desires when our engineers are designing these sensors is, as you can imagine, we want to drive the sensor as fast as possible, at as high a resolution as possible, but at the same time with the best image quality possible. And one of the things that the engineers strive for is to design a sensor that is as low noise with as least amount of any kind of ghosting or crosstalk as possible. So when we do our conversion from the very small charge in the pixel well up to the charge that is actually going to create the image, we can have as small or as large of a sensor gain, but keep the image quality as superb as possible. So every camera is going to gain up an image to some degree, but again, we at Photron, we focus on image quality, so we make sure that even though if we could drive our sensors a little bit faster, we don't want to sacrifice image quality and start putting in noise and ghosting into the image. Okay, so now you've got a very light sensitive camera. That's great. But what are some of the downfalls of having a light sensitive camera? Well, if you have a very bright event, you get saturation. And you see in this image, there's a lot of saturation. And of course, if you get saturation on your speckle pattern, you're just going to have a white object and see no contrast, see no speckles. Now this, if you are able to control the lighting, this is not an issue. If you're not able to control the lighting, maybe you're looking at some kind of a vessel or a cylinder that you're looking at the crack propagation during an explosion. Well, that explosion is a self-illuminating event, so it's possible that that's going to saturate your image. So we have a software feature called dual slope shutter. So essentially dual slope shutter gives you the ability to reset each pixel's exposure per frame at the pixel level. So essentially, if you're recording at 10,000 frames per second, for every frame of those 10,000 frames per second, and every pixel of the sensor is going to go in there, and if depending on the threshold that you set, it's going to reset that exposure value to keep those pixels from saturating. Now, it must be set prior to recording. And let me just give you a quick example of what you can expect. So this is just one of our mini AX200 cameras looking at this resolution chart. On each one of these images, the settings are the same. You notice here that we're at 6,400 frames per second for each recording, a 100 microsecond exposure for each recording, and actually the illumination of this resolution chart never changed. So here, we have way too much saturation on the right-hand side. Our dual slope shutter is off. So this is the natural image that you would see. Obviously, you can imagine if you have some speckle pattern in here, you're going to get no data there. Now this is with our dual slope shutter set at 50%. We're starting to pull up a little bit more data here, but still a lot of saturation. So now this is our dual slope shutter set at 80%. Beautiful image. This is our dual slope shutter set at 90%. A little bit too flat. A little bit, we're taking out a little bit of the detail here. So in this example, a dual slope shutter set at 80% would essentially, without changing any of your lighting situation, without changing your frame rate, your exposure time, you're going from an image that is saturated and essentially useless to a very good image with good contrast and good detail that now you can save that data, import it into the Trilion software, and get some good data. And here's just a practical example, not as from a DIC standpoint, but just a very bright, oversaturated event. You'll notice when I play this, the center recording has no dual slope shutter. the top and the bottom have different settings. And you'll see there's some saturation on all these videos at the beginning, but then at the top and the bottom, you'll definitely start to see some detail or saturation. But now where this center image is still completely saturated, the top and bottom, you're starting to see some of the flame front and the details of that, and you're starting to see this projectile exit this fireball a little bit sooner, and you're getting more detail out of this image. So again, there's no way to control that, that illumination. So dual slope shutter gives you more detail, and this can be applied to a lot of different applications, including digital image correlation. And last but not least, you know, Photron is like Trilion, a growing company. For those of you that know us, we are a Japanese-based company, and the cameras are manufactured in Japan. Photron USA is based out of San Diego. That's where all of our main operations are done. We have remote offices around the U.S. I actually work out of Birmingham, Alabama. We have another application engineer in Virginia, another one in Charlotte, North Carolina. We have an office in Indianapolis, and then we sell through local distributors and OEMs such as Trillion all over the world. And with that said, everyone expects good pre-sale support. You know, we'll promise you the world, but Photron is known for its post-sale support. And these guys at Trillion, it's not uncommon for them to call us up and say, hey, you know, I'm at a customer site and I know that the camera can do this, you know, what can we do it? And we work together as a great team. We overcome any challenges, and our goal is to make sure not just that customers purchase cameras, that you get the data that you need to solve the problem that you have. But with that said, sometimes things happen. You know, we'll have tests where a camera will get blown off a tripod, hit the deck, and well, it just doesn't work anymore. So our RMAs, our turnarounds are very fast. I think the fastest in the industry. So if something does happen, we're going to get you fixed. We're going to get you back on your feet and ready to test again as quickly as possible. And again, we are spread across the U.S. Of course, for Trillion customers, your first line of defense is Trillion. Excellent support there. But if there's anything camera specific, then we're always available for you as well. So please, you know, let us know if you have any issues, any technical questions. We'll do what we can. And with that, that's pretty much it. I didn't go into any Photron camera specific things, but if there's any questions, please let me know.
All right, thank you, Shane. I'd just like to echo that as well. We've always received really terrific support from Photron, Shane, everybody over there when we're out on customer sites or when we're working with their cameras in-house. So really terrific company to work with, and we're glad we have that partnership. Now, with that being said, we did get a few more DIC-related questions that came in over Shane's presentation. Everyone, please feel free to ask your questions to Shane regarding his cameras as well. I figured that Joe might be the best point of contact for these DIC-related questions. I'm going to go ahead and ask him some. The first one would be, for rotating fan measurements, is it preferred to use stickers? What is the downside of using speckles? Would DIC have a problem with tracking fan rotating with speckles? So Joe, I'm going to pass this off to you.
Okay, good question. So with the software will track the dots and the speckle slightly differently, but with that being said, we are able to do the speckle pattern tracking with a rotating fan. So what we would do is we would use the point in conjunction with the surface speckle pattern to get that rotating blade measurement or whatever equipment we're using for the user.
All right, very nice. Okay, we had a question come in from Carl Goodwine-Gunther. How do you pattern materials that will strain 400 to 500% strain before failure? Most paints will either crack or fade as it strains. So
the best way to pattern a specimen at that strain level would be to speckle it with dots with both the black and the white paint. Instead of using a white base coat, you can speckle on the dots, and the paint should track longer on top of your part.
okay, very nice. We're going to go ahead and move on to the last portion of our presentation today. We have John Tyson here, who's going to speak about Aramis and thermography, specifically as it pertains to the B-2 bomber that we developed this technology with. So I'm going to go ahead and set up John.
Hello, this is John Tyson speaking. We've been working Trillion for a very long time, and teamed with GOM in Germany for 20 years now. And GOM is now part of the Zeiss group, so we're really proud of the relationship we have with all the team around the world in really great ways. Wanted to talk today about not only Aramis, but how we apply this with thermography and doing thermography NDE. And this was originally developed at Wright-Patterson Air Force Base with the great teams at the Air Force Research Lab. And part of the advantage that we have working with them is shows through in this work we did with them. And so we're going to look at this Aramis thermography, and we first applied this technology, or developed it really, for studying the aft deck of the B-2 bomber program. And on the aft deck, this is an exhaust wash titanium structure that was designed to operate for 20,000 hours, but in use was only getting about 800 hours of use before fracture. We recommended an Aramis thermography capability, which we developed with the team at Wright-Patterson Air Force Base. And we wanted to first study how Aramis worked with the finite element model, and you can see an example of some of the efforts that were going on with this nonlinear thermal buckling in the materials. And Aramis nicely matched the models. But a lot of what we were measuring was thermal expansion, and so we wanted to develop a method that could subtract off the thermal expansion to the for the strain measurements to get the true mechanical strains. In order to do this, we wanted to mock up the basic capabilities. So here at Wright-Patterson, we are on a boom reaching up, looking at the exhaust of an engine, and our panel that we put in the field of view was simulating the engine wash across the aft deck B-2 and our measurement from a boom-mounted Aramis system. Of course, the data worked out very well, and the Wright-Patterson was really pleased to move on to the next step. The next step, we went and did a proof of concept test out at Wright-Patterson, out at Edwards Air Force Base. And here we have the Aramis thermography system mounted up on a boom, looking down on the aft deck of the B-2 bomber. The AFRL guys from Wright-Pat provided a precision painted materials that they were developed to perfectly match the requirements on the aft deck of the B-2 bomber. But when we went out to Edwards Air Force Base in California, it turns out that the pattern that the paint that they developed for doing the patterning did not meet California specifications. So they quickly ran down to Home Depot, got some Home Depot grill paint, and patterned the aft deck of the B-2 bomber with grill paint, and it worked perfectly. And so we had some good experience in patterning, and we just used a stencil to do the patterning and created a perfect pattern on the aft deck. The sensor itself consisted of our stereo pair and a thermal camera in the middle. And so this is your typical setup, although in a quite a ruggedized and remote application here for out in the field use of Aramis thermography. And here you can see our sensor 50 feet off the ground, looking down at the aft deck and guys in a protected situation here during the measurements. Interestingly, in the proof of concept test, the data, when the engines got up to 80% power, we lost the data from the systems, and the Wright-Patterson guy said, well, we think that we lost connection with the cameras. And our belief was that actually that the vibration from the engines running, which was their description incredible, we thought that the hard drives were losing connection, which of course became the case. We switched to solid state hard drives and fixed the problem. But the data was quite incredible. Being able to look at the thermal data and the deformation data. Unfortunately, the combined data is top secret and we can't show that. But they did use the thermal data with a correction to CTE and subtracted off of the strain data to get the true mechanical strains. So out of this test, we ended up with, the fact that all B2s had fractures in their aft deck. We developed the analytical tools at AFRL Wright-Patterson in controlled environments, and then we applied it to the operational aircraft. And AFRL thanked Trillion Quality Systems for developing this technology for them. We now apply the technology broadly to a broad range of applications. Here's an example of high-speed material testing, and we use infratech cameras. They work really well with the Aramis as an integrated package. FLIR we've been using for years, so if you have a FLIR camera, we can integrate that also. And for high-speed applications, we use the teleops cameras. And we end up with this beautiful data of temperature as well as strain, and use it for correction of the strain. But we're also able to map the true temperature in 3D coordinates, which is a really powerful capability of the technology. In certain applications, we're able to do things like look for FAD in hand layup and manufacturing. In this specific case, we have some plastic material left behind, as well as some bridging seen in our cool scan measurements. In automated AFP builds, we can be tracking the build of the material. In this case, we have a void caused by a gap between the layers beneath. But actually, we can track in between toe voids, as well as the lap gap twist, splice, that kind of thing, bond quality in our porosity, as well as things like puckering and buckling from complex motion. When we get into structural testing, we can apply Aramis to all kinds of different applications. In this case, we were used on the 787 structural testing. They had over 10,000 strain gauges in the testing, and we added 4 more Aramis systems just around the wing root area, and that wing root area we added 200,000 additional strain gauges. This was critical to the FAA certification of the 787. But now we utilize Aramis, reducing costs of structural testing. It really reduces the labor efforts tremendously, and we really end up with tremendously more and better data. Typically, Aramis allows you to see where problems exist, where traditional methods of foil strain gauges or displacement sensors, you're only looking where you believe the data, you have data that are of concern. We've also are getting into Aramis automation, where we're able to manipulate the sensor through a test and be able to look at tens of thousands of measurement points, areas in the area. Going to the really extreme areas, we can couple Aramis thermography with entire vehicle inspections, where in totally automated applications, we found that Aramis can detect barely visible damage in the for impacts and things like that, as well as internal strains that have developed. And we can use the thermography to detect the amount of delamination in the external surface. When we get into reusability of critical structures, then this is where enhanced visual inspection with Aramis thermography becomes really powerful. It's the power of trillions of strain gauges and provides a powerful tool for monitoring reusability and monitoring your vehicles over time. Just a couple return on investment kind of applications, but the most important one really is that a VP at Boeing had said, strain gauges are really costing us too much. Find a better way for reducing the number of strain gauges. With Aramis, we have a 10 times reduction in cost over broad use of strain gauges. Aramis is 50 times cheaper to apply and really affects schedule and makes things much cheaper to implement, and 100 times more data, really allowing you to find, as Justin was saying, problems where you don't even know they exist yet, and we can really solve major problems, and utilizing it for model validation as well as FAA certification and those kinds of things. Thank you all very much for your attention today. Any questions?
All right, very nice, John. Thank you so much. We did get a question come in, another question from Gregory Redwood. He asks, if you use paint for speckles, is there a template for painting the speckles, or do you just paint random sized and shaped dots?
So Aramis works very well with randomly sized dots and pattern. So what we call a stochastic pattern. This allows it to have a different pattern everywhere in the image. So it automatically locks in on the areas of interest and into the entire pattern. If we use a regular pattern, which is possible also, we typically just take a Sharpie marker and write into the pattern, which becomes part of the pattern also, but it gives us some unique areas where we can define how the measurement is aligned and all that kind of thing. But the patterning can be, when we use vinyl sheet, we create a random dot pattern in the vinyl sheet of ellipses that are all about the same size. So it creates a pseudo-random pattern in the field, and Aramis does very well with that.
All right, thank you, John. Another question came in. Any application example in the oil and gas field?
So we're used extensively in the oil and gas field for 20 years. Early on, ExxonMobil was using us extensively in their ultra-advanced pipe testing lab. And there we use typically 4 Aramis systems to look all the way around during pipe make and breaks. We actually use mirrors quite a lot now, but pipe make and breaks are quite critical to the oil and gas industry. If you have a drill pipe or other kind of casing break down hole, you can ruin the entire well. And they have to literally drill an entire well, costing millions and millions of dollars. We also worked with ExxonMobil on pipeline applications, and we helped them develop a new steel for a pipeline that was failing in Canada due to hydrogen embrittlement. And we typically a new steel took them 5 years to develop. With Aramis, we were able to develop that steel in 2 years. But we're used by companies like NOV, and the applications just are extreme in all kinds of downhole assembly applications, blowout preventers, and things like that. From everything studying rubber, seals to steel and that kind of application. Then we have applications in the refinery industry where we study a lot of pumps and motors and how they move relative to each other, even in 100-meter volumes, and be able to understand how the dynamics of these work. We can also do measurements of torque on a drive shaft in a completely non-contact way. So the applications, I could go on and on about the applications in the oil and gas industry, from upstream to downstream applications.
Okay, very good. Looks like another question here. Are there any special recommendations for making the speckle pattern for thermal imaging?
When we do thermal imaging with applications with Aramis thermography, it's really interesting that black paint and white paint actually have the same emissivity. So they really have no effect on the thermography camera. Doesn't see a black and white pattern, it just sees paint. And so it's really independent of that. But we do all kinds of interesting applications. One application on jet engine blades, we patterned with a ceramic coating because that would survive the hot section of a jet engine. And we were able to allow that measurement to, we patterned the blades, baselined them, put them in a jet engine, ran them for a year, brought them back out, and measured the creep strain on the blades. A really incredible application.
Okay, I think that actually wraps up. Oh, there's one more that had come in. I'm working on a drop test. Is there such a thing as a follower camera for DIC? Meaning, I think, John, could the cameras be moving over the course of the test?
Yes, so we're really independent of the motion of the camera. As Joe and Justin were both talking about, our motion correction capability is down to the micron level. And so our cameras can either be on bungee cords. We do a lot of work at Aberdeen Proving Grounds and that kind of thing, where the explosive blast is so violent, we don't want that shock wave to hurt our cameras. So we can just put them on bungee cords and measure the event. And by the time the shock wave hits the cameras just jump around a bit. We also do that same kind of thing on engine tests and things like that. But when we do work on like airplane to airplane type of measurements, again, we can just lock in on the other vehicle as our fixed reference, or in engine work, or we do a lot of rocket motor testing. Again, we can just lock in on the individual component that we're looking at for rigid body motion correction. Our cameras are really independent. As long as the part is in the field of view, we can track most anything.
Great. Okay.
I think that might.
Yes, I think we have a few other questions, but what we'll do, they're a little bit more technical in nature. And so if we didn't get your question today, everyone, we will follow up with you after the this video workshop in order to get you a detailed and good answer that answers your question. Thanks again for joining us. We hope you enjoyed this webinar and you found it informative. We will be sharing the presentation today as well as the materials that go along with it via email on our YouTube channel. Feel free to reach out to either us at Trilion or Shane Kirksey over at Photron if you have any further questions. Thanks again for joining us. Have a great rest of the day.